name's Eden. I'm going to talk about how to cut a ball without separating, or improved approximations for length-bounded cut. And this is joint work with my co-author Petr Kolman from Charles University in Prague. Okay, so what is length-bounded cut, or the L-bounded cut problem? Well, in this problem, we're given a graph, two terminals S and T, and some integer L. And what we'd like is to find a minimum cardinality set of edges which cut all possible paths from S to T of length at most L. So in other words, the smallest possible edge set whose removal ensures that the distance from S to T is now greater than L. Let's see an example. Here's a graph with length bound L equals 4. Those are the paths we'd like to cut. In this graph, a classical mean cut has size 3. We need 3 edges to separate S and T, but only 2 edges to increase the distance to greater than 4. Okay, so let's say these 2 blue edges cut all paths of length at most 4 in the graph. Okay, what do we know about this problem? Well, for one thing, it's APX hard, so there's no p-test. We also know that assuming the unique games conjecture, there's no constant approximation. And if we dig a little deeper, more specifically, we know that for bounded values of L, there's an omega of square root L hardness, assuming the unique games conjecture. And for this node variant, where we want to cut nodes and not edges, there's an omega of L hardness. And these are both due to Lee. I'm not going to talk much about the node variant in this talk, but we talk about it extensively in the paper. We also know approximations. So the best known approximations currently are O of n to the 2/3, and here's the number of vertices. And for the node variant, it's O of square root n. And these results are due to Pyre et al. Now, if we want to think about L as being bounded or not part of the input, then when L is equal to 3, this is easy. The problem is in P. There are various ways to see this. One way is via reduction to bipartite vertex cover. And it's already hard for L at least 4. What we know, the best approximation up until now was ceiling of L over 2. And in fact, already at L equals 4, it's APX hard. And both of these results are also due to Pyre et al. And already for L equals 4, the unique games hardness is 4/3. This is not explicitly mentioned in Pyre et al., but we observe that this follows from their reduction. Okay, our focus is going to be only on the bounded L case. So what are our results? Well, again, the best previous known approximations were ceiling of L over 2 for all L greater or equal to 4. So in particular, 2, 3, and 3 for L equals 4, 5, and 6. First of all, we improve for L equals 4, we improve the approximation from 2 down to 4/3. And note that, as I mentioned, this is in fact the best possible approximation, assuming the unique games conjecture. We also improve the approximation for L equals 5 from 3 down to 1.75. And for L equals 6, from 3 down to 2.4. And in fact, for L equals 6, this result is already a special case of our more general algorithm for all values of L, which always does better than L over 2. So comparing this to the previous best known ceiling of L over 2, for every value of L, we get a better approximation guarantee. And now you might think, since this is also asymptotically L over 2, and the previous algorithm is also asymptotically L over 2, that this is where the hardness is at. But in fact, we show that this is not true. For general L, we get roughly 0.44 L approximation. Okay. What's our approach? Well, we do LP rounding. This is as opposed to the previous algorithms, which were all combinatorial, even though the previous algorithms can also be viewed through the lens of LP rounding. Now, we round the natural LP relaxation for L-bounded cut. It's the first LP you would think of, and it's the one you could also use to emulate the previous combinatorial algorithms. So like the objective function is just summing over variables corresponding to all edges, which in the intended solution would be indicator variables for the edge being in the cut. And if we sum over edges in any path from S to T of length at most L, then that sum should be at least 1. And of course, the variables are all non-negative. So probably this LP looks very familiar to you. It's, of course, the dual of the max L-bounded flow problem. So the nice thing about this is that, in fact, all our algorithms not only give approximation guarantees and improved approximation guarantees, but they also give matching upper bounds on the L-bounded flow cut gap. So the gap between the smallest L-bounded cut and the maximum flow along edge paths of length at most L. So even if you don't care too much about approximations for this problem, so you'd have to ask yourself while you're watching a talk at Approx, you might care about combinatorial guarantees like flow cut gaps. Okay, so again, these are our results, and I'm going to start by describing our approximation for L equals 4, which, as I mentioned, is a 4/3 approximation, improving over the previous best known 2. And before I talk about that approximation, I just want to see one way of understanding why the problem is easy for L equals 3. So why is that the case? Well, there are various ways to see this, as I mentioned, but one of them is also via this LP that I described. So here again is that linear program or LP relaxation, specifically for the case of L equals 3. So why is there no integrality gap? Why is this integral? Well, one way to see this is to check that the constraint matrix is totally unimodular. But for us, the more interesting thing is that there's a randomized rounding, which is lossless. And this is also a very natural rounding. This is the typical sort of level cut or ball cutting algorithm. So we map every edge to an interval between 0 and 1 of length, which is at most the corresponding LP value. So as an example, we have these edges here, then edges incident in S or T are going to be mapped to intervals which start and end at 0 and 1 respectively. And if you have an edge which is a middle edge, it's not incident in S or T, then we just sort of squeeze it between these two intervals. And the LP constraints guarantee that the length of this middle interval will be at most the LP value. And now we sample a uniform radius between 0 and 1. And we cut every edge whose interval contains this radius. So in this case, we would cut UV. And of course, since these intervals have length, which is at most the LP value, then in expectation, we don't pay more than the LP value. Okay. So why can't we extend that algorithm to also work for L equals 4? Or what breaks down? Here again is the LP. Well, the nice thing for L equals 3 was that in paths of length at most 3, every edge can only be really in one position. It can either be a left edge, a right edge, or a middle edge. And once you have paths of length 4, the same edge can appear in different positions in different paths, which means that if we want to map it to intervals, we might want to map the same edge to 2 different intervals. As an example, consider this graph, similar to the graph we saw before, and consider this LP solution. If you want, you can pause the video for a minute and check that this is a feasible solution. Note that the optimum here is 2, so this is a graph which gives the optimal integrality gap of 4/3. But more to the point, the edge, the middle edge, UV, can be mapped in 2 different ways to an interval, right? So if we think of UV as the second edge in a path from S to T, such as this path, then we would want to map UV to the interval ½1. But if we think of UV as the second to last edge, in a path, for example, this path, then the natural mapping would be to map UV to the interval 0, half. So two completely different intervals corresponding to this edge. Okay, so what do we do for L equals 4? Well, we resign ourselves to the fact that we're not going to find one natural mapping of edges to intervals, and we map every edge to two different intervals in the natural way. So for every edge which is not incident in S or T, in which case both of the intervals will be the intervals I described before. We choose two mappings. One corresponds to where you would place the interval if UV is the second edge in the path from S to T, and the other one is where you place the interval if E was the second to last edge in the path from S to T. Okay. And now again, we sample uniformly random radius between 0 and 1, and we cut every edge which is in at least one of the two, such that R is contained in at least one of the two intervals that this edge is mapped to. Right? So for example, here, R falls in one of the two intervals corresponding to E, and we cut edge E. Okay. And this is a 2 approximation, right? Now the probability of cutting an edge E is at most the probability that we will hit one of two intervals of length XE, so it's 2XE instead of XE. And we already had a 2 approximation, right? I promised you a 4/3 approximation. So we can do a very simple thing, only do this with probability 2/3, and then the probability that we will cut an edge E is at most 4/3 XE. So evidently that's a 4/3 approximation. Of course, with the caveat that it seems that with probability 1/3, the algorithm just destroys reality, and then you don't have to worry about approximating anything. So if you're not happy with that, then with probability 1/3, you have to do something else. So let's see what we do. In this case, in this cut, we don't sample one radius, but rather two uniformly random radii, one between 0 and half, and one between half and 1, and they're correlated. They're exactly distance half apart. And now we have two criteria for cutting an edge. We either cut an edge if one of these radii falls in the intersection of the two intervals corresponding to the edge. So for example, here, the first radius falls in the intersection of the two intervals. Or we cut the edge if both of the radii appear in one of the intervals. So for example, here, R1 and R2 both fall in JE, one of the two intervals assigned to E, and then we cut edge E, and it's okay if it happens in both intervals, but it should happen for at least one. Okay, so these are the two criteria for cutting an edge in the second cut. Okay, now why is this algorithm even correct? It's not immediately clear. It is sort of clear for the first cut, which we choose with probability 2/3, right? This is just something that follows from our LP constraints. So right, if we take, without loss of generality, the path of length 4, then its edges are mapped to 4 intervals, possibly more, but at least these 4 intervals that completely cover the interval 0, 1. So then if we choose a radius between 0 and 1, we're going to cut at least one of the edges. In this case, we cut 2 edges in this path. But it's much less clear for the second cut. So I want to focus on the second cut. And again, the criteria for cutting an edge in the second cut is either one of the radii appears in the intersection of the two edges corresponding, so two intervals corresponding to the edge, or both of the radii appear in one of the intervals corresponding to the edge. So again, let's look at a path of length 4. And the same intervals that we looked at before corresponding to the positions of these edges in this specific path. And I first want to note that if one of the radii intersects either the interval corresponding to the first or last edge, then we're done, because those edges have two identical, or mapped to two identical intervals, right? So then, for example, if R1 intersects one of the intervals corresponding to E1, it in fact intersects both of them because they're the same, and then we would cut E1, okay? So otherwise, they intersect the middle two intervals, and I'm skipping the case where they both intersect just one of these two intervals because that would be a case where by the last criterion, we cut that corresponding edge. That would be an interval that contains both radii. So each one is contained in a different, in an interval corresponding to a different edge. And now each of these edges also has an additional interval associated with it. So if the radius which cuts that interval also cuts the second interval corresponding to that edge, then by the first criterion, we would cut that edge. So for example, if R1 intersected both IE2 and JE2, then we would cut E2 and we'd be done. So finally, assume that this also doesn't happen. And in this case, I just want to stop for a second and understand why there would be two distinct intervals assigned to an edge. And right, the reason is that, for example, edge E3 could be not only the second to last edge in a path from S to T, but also the second edge. So there would also have to be an edge from S to V, and similarly, there's also an edge from V to T because of the two possible positions of E2. So the graph also has these two additional long blue edges, and I just want to look for a second and see what intervals these edges would be mapped to. So by our construction, if you pause for a minute and think about it, you would see that these edges would be mapped to two very long intervals, which completely cover 0, 1, and both of which contain both radii. So they have an overlap of length at least half, which means that at least one of these two intervals has length at least 3/4, and so at least one of the two LP values corresponding to these blue edges must be at least 3/4. Now, I never said that that can't happen, right? There's no reason why the LP might not want to assign such a large value to some of its variables. But this is a case that we can avoid because we can start with a pre-processing step that cuts all these edges in advance. And then we don't have to worry about this case, and then the algorithm is correct. And the reason is that we're shooting for a 4/3 approximation, so it's always okay to just cut all edges with LP value at least 3/4 before we do anything else. Okay, so that's correctness. Let me talk briefly about the approximation guarantee. So first, consider a short edge. A short edge is an edge with LP value less than half. Such an edge, and for such an edge, this last criterion can't happen, right? It can't be that one of the two intervals associated with it contains both the radii, because the radii are at distance half from each other, and the edge is short. So let's look just at this portion of the algorithm and analyze the probability that we cut a short edge E. So in the first cut, it's easy to see that it's basically the length of the union of the two intervals, right? It's the probability that R falls in this union. And in the second cut, it's the probability that at least one of the radii falls in the intersection of these two intervals. But because these radii are sampled uniformly within intervals of length half, then it's not, the probability is not the length of the union, but twice the length of the union, okay? And now if we put it all together, then we have probability 2/3, right, the length of the union plus with probability 1/3 twice the length of the intersection. And all in all, we get 2/3 times the sum of the lengths of the intervals, which is 4/3 times the LP value of E, since both these intervals have length XE. Okay, so that's for short edges. And now if you now consider a long edge E, an edge with LP value at least half, and just stare at this beautiful figure from our paper, which somehow explains everything, but I don't have nearly enough time to explain it right now. So if you'd like to hear more details, you can read the paper. Okay, so that's our approximation for 4/3, for L equals 4. I could talk about our approximation for L equals 5, but it's 10 times more complicated with a very long case analysis, so better not do that. I can also talk about our asymptotically best result, but it's also not the most elegant result in this paper. So since this is my talk, I'm going to talk about our algorithm, which is best for smaller values of L. I really love this algorithm. It's simple and it's elegant, and if there was any justice in this world, this would be the best possible approximation, and unfortunately it's not. But I'll tell you a little bit about it. So it's based on a recursive LP rounding algorithm, and it has the following recursive guarantee. It transforms any alpha approximation or alpha rounding for L-1 bounded cut to this complicated expression approximation for L bounded cut. So if you sort of combine this theorem with our 7/4 approximation for 5 bounded cut, then you get our guarantee. So let's look at the algorithm. It takes as input an LP solution X and a length bound L. Again, if L equals 5, then apply our 7/4 approximation, which I'm not going to tell you about right now. And otherwise, we define these new values. This is not an LP solution for the relaxation for L bounded cut. But if you think about it for a minute and you use the convexity of the function t over 1 minus t, it is an LP solution for the relaxation for L-1 bounded cut. So we take advantage of that and we recursively apply our rounding for L-1 bounded cut with these new LP values. And then we get some cut f prime, which cuts paths of length at most L-1, meaning if we remove f prime, then now the distance from S to T is at least L, and we only need to cut shortest paths. And once we only need to cut shortest paths, it's very simple because we can apply the standard rounding on the remaining edges in the graph to get a minimum cut in the layer graph or the graph of shortest paths from S to T. And now we just return both edge sets, the first one in order to cut paths of length at most L-1, and the second one which cuts the remaining paths of length L. Okay. Sorry. Okay, so let me talk about the approximation guarantee for a minute. As I mentioned in the last step, the min-cut rounding is exact, so we get a set F of cardinality, which is at most the LP value of the edges excluding f prime in the remaining graph. So right, it's the LP value minus the LP value of f prime, which means that the final cut has cardinality, which is the LP value plus the cardinality of f prime minus the LP weight of f prime. So we need to bound this last expression, the cardinality of f prime minus its LP value. So how do we do that? Well, let's bound its expectation. What does a single edge contribute to this, the expectation of this expression? Well, it contributes the probability that the edge appears in f prime times 1 minus the LP value of the edge. And if we assume that our recursive rounding is an alpha approximation for L-1 bounded cut, then this is at most alpha times xe prime times 1 minus xe, because a recursive call uses x prime, not x, as the LP assignment. And if we plug in the definition of x prime, then this is the expression we get, which now has x instead of x prime. So summing over all edges, the expectation of the cardinality of f prime minus its LP value is at most this expression, quantity 1 minus 1 over L-1 times alpha times the LP value. And so the final cut has size, which is at most LP plus this expression. And you'll note that this is exactly the approximation guarantee that I promised you. Okay, turning to open problems. So we've essentially resolved four-bounded cut if you believe the unique games conjecture, and if you don't believe the unique games conjecture, then maybe you'd prefer to think about that and not about four-bounded cut. It would still be interesting to get tight or tighter approximations or hardness results or even flow cut gaps for any value of L, which is at least 5. And it's an interesting question whether the edge version is easier to approximate than the node version. We don't know. We know it's not true, assuming UGC for L equals 4, but it could be true in general. We don't know if the undirected version is easier than the directed version, so that's also worth exploring. And it's also interesting to think about the problem for unbounded L, where L is part of the input. So again, there we only know O of n to the 2/3 and O of square root n for the node version. So it'd be good to get any improvement over the current best algorithms or any improvement in the hardness, which even for unbounded L, all we know is still APX hardness or no constant, assuming the unique games conjecture. Okay, that's all. Thank you very much.